All right, we are starting. We are going to rock on to Electric Avenue. And I want to talk today about life in moving fluids. Things that live in the ocean live in water. Duh. That seems pretty obvious. And it's useful to look a little bit at the physics and the engineering of water itself and the forces that living things are exposed to. You probably, I hope, remember from distant chemistry classes that water molecules are polar. There is a slight positive charge on one end and a slight negative charge on the other because of the bond angle between the nucleus of the oxygen atoms and the nuclei of the hydrogens. They're not in a perfectly straight line. That gives the water molecule a slight electrical charge, and that means water molecules tend to cohere, meaning that the positive end of one water molecule will be attracted to the slightly negative end of another water molecule. I assume you have heard of this before. So water molecules don't behave quite like sand grains. They do have this stickiness. And you can model the flow of water as, imagine it's made up of a huge number of extremely thin sheets. Every sheet is made up of water molecules that are bonded to each other. And then when water flows, each sheet slides over the sheet below it. A little bit like if you were to take a pack of cards and then kind of sweep it with your hand and get the cards to fan out over the surface of the table, right? Each card would slide over the top of the card below it. And then the card below would slide over the top of the card below it, and so on, until the cards had all fanned out. So you can model the flow of water as being like this stack of very thin sheets of bonded molecules. But the sheets have friction because each sheet is forming hydrogen bonds with the sheets above it and the sheets below it. So, if you're fanning a pack of playing cards, usually those are coated with plastic, so the cards have very little friction. But if you were panning a pack of cards made out of construction paper or something like that, those are rougher, and there would be more friction between sheets. So these sheets, you can imagine sliding past each other, but there's friction between them caused by hydrogen bonding between water molecules on adjacent imaginary sheets. And so when a force acts on water, when water gets pushed by something or shoved aside by something, the upper sheets drag the ones below them along. And that causes water to be placed under a type of stress called shear stress. There are three basic types of stress that something can be under. Compressive stress is when you're squashing something. Compressive stress is what columns on a building are under. They're being pushed by the force of gravity. Tensile stress is being pulled apart. So a tight wire or a rope under tension, a cable under tension, a guitar string, all of those would be under tensile stress. Compressive stress is, of course, something being squeezed. A piece of furniture that you're sitting on would be under compressive stress. Shear stress is stress that tends to, how do I want to put this? Distort something in a sideways direction. That's not a very good way of putting it from an engineering point of view, but it's the best I can think of at this moment. Water is placed under a stress that makes it slide past itself. And water is somewhat resistant to it because those imaginary sheets of water molecules are sticking to each other and have a certain amount of friction. This means that if you have a fluid that is very physically well behaved, it's called a Newtonian fluid. It flows according to some basic physics worked out by Sir Isaac Newton way back when. There's a lot of fluids that don't perfectly match this. We don't really need to get into that here, but this will do. And a Newtonian fluid, right, if it's touching a solid surface, right at the surface, it doesn't flow at all. We call this the no-slip condition. And so the sheet of water that is right next to whatever the water is touching, whether it's a rock or the wall of a pipe or the bed of a river, whatever it is, right there, the water isn't flowing. That lowest sheet of all doesn't move. But the sheet above it moves a little, and the sheet above it moves a little more, and the sheet above it moves a little bit more. So the imaginary sheets of water molecules that are close to the surface are slowed down. And the upshot is that there's a zone of slow flow close to any solid object touching the water, close to the walls of the pipe that it's flowing through, the walls of the tank that it's in, close to the rocks on the bottom of the sea, whatever it might be. It's also close to whatever solid objects are moving through the water, the skin of a whale or the hull of a submarine, whatever it is. You have this zone of slow flow close to any surface. And that zone of slow flow is called the boundary layer. It's represented, I'll never make you do calculations with this. If you really want to, you probably ought to take a course in fluid engineering, which I don't think we offer here. But I'm not going to make you calculate this, but it's represented in this diagram by a lowercase Greek letter delta. And it's the zone within which flow velocity is less than 99% of free stream flow. So free stream flow is what's the flow far away from any surface. You know, what's the flow right in the middle of the river channel, way off the bottom? How fast is it going? So the zone where flow velocity is 99% of that or less, we call the boundary layer. That can be a little counterintuitive if you haven't spent a huge amount of time in the water, but air does it too. And in fact, air and water, I mean, one's a gas and one's a liquid, but they're both fluids. Fluid just means something that flows, and air flows just as water flows. And a lot of the math that applies to one applies to the other. And air in particular has boundary layers, and you can feel these on a windy day at the beach. If you're standing up and, you know, jumping around playing beach volleyball or whatever, you can feel wind on your face on a windy day. If you lie down, you feel a lot less wind. I mean, it doesn't even have to be a beach. You could go outside and feel this. You feel more wind force when you're standing tall than you do when you're close down to the ground. And I noticed this a couple of years ago. You can also see this with fireworks smoke. If you send up a rocket, as I'm sure many of you do on the 4th of July, if you just send a rocket straight up, the rocket will, of course, shoot straight up. It will leave a smoke trail behind. And you'll see that smoke trail high in the sky will usually disperse pretty rapidly. It'll get carried away. But the smoke close to the ground won't move nearly as fast. And that's because you're in the air boundary layer. your air gets slowed down by friction with the surface when it's close to it. So there. I mean, you can feel it if you go scuba diving or something like that. If you go scuba diving in heavy weather, you can get tossed by winds this way and that when you're close to the surface. But once you get down to the bottom, you don't feel it at all. And you can feel this skin diving as well. But you can certainly feel it in air, even if you can't swim. That boundary layer is a barrier to distribution of heat and oxygen. It is, since it's not moving as fast, living things in the boundary layer may use up the oxygen that's present and not get fresh supplies moving in nearly as rapidly. So if you're a marine organism and you're stuck down in the boundary layer is not moving rapidly. It's not bringing in fresh supplies of oxygen or nutrients or things like that. And so marine organisms that depend on oxygen transfer and, maybe bringing in foods as well, often have very erect shapes that stick up out of that boundary layer, like this soft coral right here. On the flip side, these are limpets. They're snails with cap-shaped shells. They're not coiled. They're just little caps. And limpets are typical of very rocky coastlines and often live in places where waves are breaking. So they may be exposed to extremely fast and violent currents. Maybe not on a steady basis, but certainly if a wave hits that coastline, they're going to take a lot of force very quickly. And one of the ways they can minimize the risk of getting swept away and, bashed to pieces or otherwise destroyed is by hunkering down in the boundary layer as low as possible. So a lot of marine organisms that are exposed to strong currents on rocky shores develop these very low down profiles, limpets and chitons and barnacles and things like that. The same species of limpet might grow lower where the currents are really strong and maybe get up a little higher where the currents are not as strong. So that's the idea of the boundary layer. And some organisms adapt to try to get out of the boundary layer and get up in the full force of the stream because water currents might be bringing in oxygen and food and things like that. Others hunker down in the boundary layer as a way of avoiding the full force of current flow. And now we need to meet a fellow by the name of Osborne Reynolds. Here he is. He was the first ever professor of engineering in the United Kingdom. And among other things, he got interested in the flow of water through pipes. And he built a gizmo that sent water through a glass pipe, and he added a very narrow nozzle to it that injected a stream of dye into the water. So that he could trace the flow. And here's some diagrams that he got. Up there, A is what Reynolds got at slow flow speeds. You have the dye injector is on the left. The glass pipe is this is the kind of trumpet-shaped thing. And inside the glass pipe, you can see there's basically just a single thin stream of dye, and it stays a very thin, smoothly flowing stream all the way to the end of the pipe. By the way, we call that laminar flow. Laminar, by the way, comes from the Latin word for a plate. So remember those imaginary sheets of water molecules that I talked about. If you pretend, I talked about sheets, but if you think of those as being like flat plates, sliding past each other. That's what laminar flow is. But Reynolds found that if you increase the speed of flow through the water, the flow would suddenly turn turbulent. It would suddenly start churning, making whirls and whirlpools and making clouds. And he discovered by illuminating it with a very quick flash of light, he could see eddies in the turbulent flow. Eddies, little areas of spiral flow, little curlicues of flow. You can see these again if you've ever just watched some smoke on a fairly windy day. If the wind is blowing fast enough, the smoke will start making little swirls. Those would be eddies. And Reynolds found that the transition from very smooth laminar flow to turbulent flow happened fairly quickly as he increased the flow speed. And he worked out that the switch from laminar flow to turbulent flow always happened when a particular combination of factors reached 2000. And that combination of factors is called the Reynolds number. Don't memorize this formula. This is just what it looks like. It is velocity times length times density of the fluid divided by lowercase mu is something called dynamic viscosity. What the heck is all that? Velocity is the speed of flow. Be it said, you can apply this to other situations than fluid flowing in pipes. V could be the flow speed past something that's holding still, like the rocks on the bottom of the ocean, or it could be the speed of a moving object relative to the fluid that it's in, like a fish swimming through water. L is something called characteristic length. If you're talking about pipes, L is the diameter of the pipe. If you're talking about something that's not going through a pipe, L is the diameter of an object moving through the fluid. So the diameter of the fish or whale or sheetagnath arrowworm or whatever it is going through the water would be characteristic length. Greek letter rho is the fluid density, and I assume you know what that is. Greek letter mu, the dynamic viscosity, is the amount of energy that's required to make those sheets slide past each other. It's a measurement of the resistance to flow, and you can intuitively think of this as how gooey the fluid is. It doesn't take that much energy to make water molecules slide past each other. It takes a lot more energy to get molecules of maple syrup or motor oil or Heinz slide past each other. Those stick to each other a lot more. And the energy required to move them past each other is greater. And yeah, intuitively, you can think of this as how gooey the fluid is. Something like water or alcohol has a relatively low dynamic viscosity. Something like syrup has a much higher dynamic viscosity. And again, if velocity times characteristic length times density all divided by dynamic viscosity, that gives you a number called the Reynolds number. It's usually not necessary to calculate this very accurately. But if the Reynolds number is greater than 2000, flow is going to be turbulent. If it's less than that, flow is going to be laminar. There's a bit of a transition stage in between there, but there's a fairly sharp switch from laminar flow to turbulent flow. And the cool thing about this is that if you have two situations, like an airplane in the real air and a model in a wind tunnel, If the Reynolds numbers are the same, the flow patterns will be the same. So think about this. There's a model of an airplane in a wind tunnel. How do we know that the flow around the model is similar to the flow that a real airplane would experience? Well, there's our formula. The length is less, right? The model is smaller than the real airplane. But if we can make the velocity greater, then that will cancel out the smaller length and the Reynolds number will be the same. So we have to blow air past this model much faster than a real airplane would experience, but that's compensated for by the fact that this has a smaller characteristic length than a real airplane. And so like if this model is half the size of a real airplane, but the air flowing around it is twice the speed, that means that air will flow around the model in the same way that it would flow around a real airplane. We call this dynamic similarity. That's the secret behind testing models in wind tunnels, or for that matter, we can even test them in flow tanks. You can see a model car there. That car is immersed in water, and there is a little gizmo that's injecting streams of dye into water, and the water is flowing past the car. So you can see the flow pattern around the car. You can see there's a lot of turbulence behind the car. And as long as you juggle the numbers in such a way that the Reynolds number is kept constant, then the pattern of flow around this car will be the same as the pattern of flow around a real car in air. So yeah, you can test model ships in wind tunnels. You can test model cars in flow tanks as long as the Reynolds number is kept constant, which I happen to think is pretty cool. Let me see. This thing would be, okay, the car is going to be a lot smaller, so L is going to be smaller, but the density is greater. Water is a lot more dense than air. So the smaller car is made up for by the increased density of the fluid. There's also a different dynamic viscosity, and off the bat, I don't remember what it is. But as long as you keep the overall Reynolds number the same, the flow in the flow tank of water is going to look the way that flow in air around a real car would look. I hope that's sort of clear. And you can actually see this in your own kitchen if you turn your faucet on. If you have just very slow flow from a faucet, it looks very smooth. And that's because the water isn't moving fast and flow is laminar. If you speed up the flow starts looking a lot more turbulent, and you can see that the stream no longer looks nice and smooth and glassy. In fact, try this sometime. Turn your water faucet on to a very slow flow. Close to where it's coming out of the faucet, it will look laminar. It will look like this very smooth, almost like a smooth piece of glass. That's because right where the water is coming out of the faucet, it's not moving very rapidly. But as that water falls into your sink, it accelerates because that's what gravity does. And somewhere about midway down that stream of water, you'll notice that it starts looking more turbulent. Instead of having a smooth surface, you'll actually see ripples and turbulence on the surface. The stream will look very smooth where it's going slowly, and more turbulent once it has accelerated to a higher rate of speed thanks to the acceleration due to gravity. It's counterintuitive, but you can see consequences of Reynolds' discovery all the time. So Yeah, I should assign that as homework. Everybody go and turn on your water faucet and stare at it. You can rewrite Reynolds numbers. We don't really need to do this here. I'm not going to make you solve any problems or relations in this class, but the Reynolds number is the ratio of inertial forces to viscous forces. It's the ratio. Inertia is right. Objects in motion tend to stay in motion. So inertial forces you can think of as the tendency for molecules to keep moving. Viscous forces is the tendency for molecules to stick together. And the Reynolds number is the ratio between the two. At very low Reynolds numbers, viscous forces predominate. The molecules stick to each other very well. It takes a great deal of energy to make them slide past each other. Flow is very smooth, and vortices don't form. And if you don't know what a vortex is, there's one of them hitting South Alabama right about now. A vortex is a spiral pattern of flow, okay, like a hurricane. Like the unseen spiral patterns of flow that make dry leaves behind your car jump up and whirl around as you drive past. Okay, that's the best mental image I think I can give you. At very high Reynolds number, flow becomes turbulent, vortices form, and inertia predominates. The Reynolds number of a large whale swimming at 10 meters a second is 300 million. The Reynolds number of a bacterium swimming at 10 microns a second is that's what? 1 times 10 to the minus 5. So Reynolds numbers can exist over, maybe 12 different orders of magnitude in the biological world. That's a fancy way of saying that the type of flow that a whale feels is very different from the flow that a swimming bacterium is exposed to. They're exposed to very different kinds of forces. They've got drastically different limitations on what they can do biologically. They might as well be living in different worlds. So when you go swimming in water, you're swimming at a pretty high Reynolds number. Michael Phelps, swimming in fresh water at, let's say, 20 Celsius is what? 65 Fahrenheit, 70 Fahrenheit. Yeah, 70 is close enough. The Reynolds number is about 3.5 million. That's a lot higher than that 2,000 limit. So the flow is turbulent. All right, he's churning up the water. There will be vortexes, places where the water is spinning off into spirals around him. Now consider something like this. This is the larva of an invertebrate called a. It's quite pretty. Looks like something you should hang on your tree. And being 200 neurons, roughly 10,000 times smaller than you are. Now think about dynamic similarity again. The acorn worm larva and Michael Phelps might be swimming in the same body of water. I mean, not in a chlorinated pool, but if Michael Phelps happens to be swimming in the ocean, they might be swimming right next to each other, but the larva's not experiencing what Michael Phelps is, because the flow pattern that larva experiences is the same as the flow pattern that you would feel if you were swimming in a liquid with a dynamic viscosity 10,000 times greater than water. So what this larva is undergoing is the same kind of flow that you would undergo if you were swimming in Hershey's chocolate syrup, more or less. Flow is much more laminar. It flows much more smoothly. There is there aren't any vortices. The water isn't swirling around a little bit. Water molecules tend to move in straight lines. One of the effects is that coasting distances are much shorter. If Michael Phelps suddenly stops swimming, he can still coast for a while. If this larva stops swimming, the larva will come to a pretty abrupt halt. And it's even worse if you're a bacterium. The flow pattern that a bacterium experiences swimming through water is roughly the same as the flow pattern you would experience if you were swimming through asphalt. Okay, no vortices, no swirling, no turbulence, very, very smooth flow. And someone calculated that if a bacterium were to suddenly stop swimming, its coasting distance would be roughly the diameter of a hydrogen atom. So yeah, essentially bacteria cannot coast at all. They've got no inertia, right? If they stop swimming, they don't stay in motion at all. That's the kind of world that they live in. Water to them feels like swimming in asphalt would feel to you. So even though the bacterium and the acorn worm larva and Michael Phelps might be swimming in the same body of water right next to each other, they're not feeling the same type of forces. The water is not going around them with the same effect. They're subject to very different types of stresses and pressures. One of the practical effects of this is that microscopic organisms have much slower sink rates than larger organisms. Right? A person thrown into the water has to keep swimming, or he or she is quite likely to sink and possibly drown. Microscopic organisms don't sink nearly as fast. And this is one of plankton's secrets for how they can stay at the surface even if they're not able to swim. Some of the critters that you're looking at here, this is more ocean plankton. Some of them are algae and can't swim at all. Others, like the dinoflagellates that are kind of just below center, can swim, but maybe not very strongly. There is a small jellyfish at the upper left and a sea urchin, probably larva at low center. Those can swim a bit, but they can't swim very strongly. Part of the secret to their success is simply that they're very small. So they've got such a slow sinking rate that, sinking down to the bottom and dying down there is less of a concern than it would be for something shaped like you. Okay. A force that acts opposite to the direction of motion or relative flow is called drag. So if you have an airplane flowing through the air, gravity is the force that tends to pull it down. Lift is the force that pushes it up, caused by air flowing over the wings. Thrust is the force applied by the engines that pushes it forward. Drag is the force that tends to push it backwards. The force that's applied by various types of resistance that air has to things flowing through it. There are the same thing applies to water as well, by the way. Ships would also experience drag, the force that tends to oppose the force that their engines are putting out to get them to move forward. There's many different sources of drag. Friction drag is caused by friction between the fluid and the surface. The more surface area something has, the greater the friction drag it will experience. Pressure drag is caused by the fluid's inertia. That tends to be caused by the fluid basically hitting the front of whatever is moving through it. That's proportional to the cross-sectional area of the object and also to the Reynolds number, but let's not worry about that. You also have induced drag caused by vortices, and I'll show you what that looks like in just a minute. What you're looking at here is a diagram of a flat plate, right? Like a, very thin plate made out of metal or something like that. And the blue lines are called streamlines, and they represent water moving around this flat plate. Now, the flat plate is not presenting much area broadside to the flow, right? It's slipping through, but it also has a lot of friction drag. It's got a very large surface area that's exposed to the water, right? A lot of surface means that there is friction between the flat plate sliding through the water and the water that's flowing around it. Now, if I took this same shape and turned it right angles, I'd still have a lot of friction drag, but I'd also have a lot higher pressure drag, because now instead of hitting the water narrow edge on, it's hitting it broad edge on, right? All of that surface area would now be facing right into the flow. And so that same shape is going to feel much greater force pushing it backwards in the direction of flow. I should probably make a diagram of that one of these days, but I hope you can visualize. Imagine taking a flat plate and rotating it so that the widest dimension is facing the current head on, and you could see that thing would be, subjected to a great deal of force as the water's hitting it broadside on. If you have a sphere or a cylinder that's going through, it experiences a lot of pressure drag because it has a bigger cross-sectional area. So this flat plate, if it's flat and it's meeting the flow narrow edge on, it has plenty of friction drag, but it doesn't have much pressure drag. This is going to experience more pressure drag because it's got larger cross-sectional area. And the other thing that's going to happen is, look at the vortices in the back. At high Reynolds numbers, one of the weird things that happens is that the flow around a sphere will break away from the surface. Water will hit the front of a sphere or a cylinder, go above or below the cylinder, and if flow is slow, the flow will go around the cylinder and come back to the back of the cylinder and then go on. That's what you're seeing in situation 1, ideal. But look at situation 4. What's happening is that fluid is hitting the cylinder, going around it above and below, and then going off straight instead of going back around the cylinder and rejoining. It's going around the cylinder and then going off straight, and that creates literally negative pressure behind the sphere. There's a zone where water isn't flowing at all that creates negative pressure, and that literally sucks it backwards. At situation 4, it's saying laminar separated flow. Once the flow is going fast enough that you have flow separation, your drag starts increasing a great deal. One of the weird things is that if you increase turbulence in the boundary layer and make the surface of something rough, you can actually delay the onset of flow separation. Back maybe like 150 years ago, golfers discovered that hacked up golf balls, that had been hit a lot and, had surface damage, actually traveled farther than brand new smooth golf balls did. And as a result of that discovery, golf balls are now made rough on the surface deliberately. This is why golf balls have dimples. Creating a little bit of turbulence in the boundary layer actually delays the onset of flow separation. So a smooth golf ball will actually suffer more drag than a dimpled golf ball and a smooth golf ball won't go as far. That's kind of weird. One of the things you can do with baseballs is if you make one side of a baseball smooth and the other side of a baseball rough, that means that the flow going around the baseball is not equal on both sides. Yeah, you'll get flow separation on one side, but not on the other. And that tends to make the baseball break in funny ways. This is illegal, by the way, but occasionally you'll see a pitcher get disciplined because he's got a little emery board, the little stiff sandpaper type thing you might use for finishing your fingernails. If he roughens one side of the ball but not the other, he can actually cause the ball to break in strange ways. And you're not allowed to do that now. That's illegal. But occasionally you'll find pitchers that try it. And they're using the same principles as golf balls, but by only roughing one side of the baseball, they can throw it and make it break in ways that will confuse the heck out of the batter. Or that's the idea anyway. So, what's the best shape for something traveling through water? Well, if you have a sphere, right, you have the problem of those vortices. And if you look at situation 4 again, back behind the sphere, you have that area of negative pressure where the flow is not sticking to the sphere, and you have all of those vortices, all that swirling back behind the sphere. So if you take a sphere and you squish it a bit so it's not presenting quite as much area for pressure drag, and you stretch it out so that it's filling up that space where those vortices would be, you end up with a shape like this. You now don't get flow separation because part of what used to be a sphere is now filling the area where that flow separation would happen. You've squished it down enough that you're not getting quite as much pressure drag. And a shape like this is basically the mathematically lowest drag shape that is possible to make. It's called an airfoil. And it is, in fact, the shape of airplane wings. This is, in fact, a cross-section of a wing shown in a wind tunnel, and the parallel lines that you're seeing are streams of smoke being released. This is the shape that minimizes drag. This is the most efficient shape that you can make something for traveling through any fluid. So it's the shape of airplane wings, the shape of airplane bodies, the shape of bird bodies, the shape of bird wings in cross-section, the shape of boats and, submarines and things like that. And also the shape of any living thing in the ocean that has to swim fast. Down on the bottom here, that's a dolphin. In the center, that's a shark. Up top, that is an extinct marine reptile called an ichthyosaur. And you'll notice that they've all got the same body shape. And that body shape is very close to that ideal airfoil shape. If you want to make something, if you want to evolve a body that's got as little drag as possible, which means that it has maximum efficiency in movement, it gets the most movement possible per unit of energy expended, you pretty much have to build it like an airfoil. So you'd see this in sharks, dolphins, you'd see it in fast swimming fish like tuna, you see it in salmon, you see it in, I don't know, barracudas and wahoos and things like that. Any fish that is any critter that's built for speed, any critter that has to travel with maximum efficiency through the water, be it a shark or Los Angeles class attack zone, have to be built to this shape. This is the most efficient way to minimize drag in various places. Somebody actually measured there is a fishing bat, and even the toes of a fishing bat are shaped like airfoils. On the other hand, want to be shaped like an airfoil because you want to increase drag. Right? An airfoil is a good shape for moving through fluid very, very fast, which means it would be a lousy shape for a parachute. Right? The idea of a parachute is that you do not want to be moving through the air very, very fast. So high drag designs would be things like milkweed seeds and dandelion seeds, a lot of plankton. The thing at the bottom is a single-celled critter called a planktonic foraminiferan that's got a very high drag shape because being planktonic, it doesn't want to slip swiftly through the bottom. It wants to stay up in the water. A lot of filter feeder they don't need to slow their flow themselves down, but they're trying to slow down flow of water so that they can pick food particles out of it, and they have very high drag shapes. And again, parachute where you don't want to fall to the earth. It's with ruthless efficiency, you want to stay up. So there are a lot of cases where high drag designs are very desirable, in cases where low drag designs are desirable, and selection has acted in all of these cases to develop a form that is preferred for a particular function. Okay, hope that was reasonably clear. I'm going to go ahead and stop the recording. Once I'm done with that, I'll take any questions that you might have.
I do.
And somewhere in this mess, there. I will stop the recording now.